They tell us here that there's a reaction force of 400 newtons. So they're on some force plate, basically a scale. So it's telling us what that normal force is, 400 newtons. And we do want to explicitly put here that the net moment around A is 0. Once we're back in equilibrium problems, that will be the case, that if we take the sum of moments, it will be 0. Here we do want to explicitly put that. And we want to find the force in the Achilles tendon such that we are in equilibrium, according to this diagram. So we want to find the value of what they are calling Ft. Right, so I want to make sure that in my diagram, whatever I'm calling them here, that the diagram is going to match that. Now in this section, I'm not going to call it a free body diagram because it won't have all the things necessarily that we need in a free body diagram when we get to rigid body. So I will just call it a diagram for right now. Anytime we're in equilibrium, it will be a free body diagram. In this case, we're not quite there yet. That's in section 5. We'll get there. So I do want to represent this situation much the way we have been, but a little bit looser, just calling it a diagram. Now here we have a rigid body. It's not just a particle. So we need to represent kind of all the, not everything is happening at, say, point A, but we do know that the net moment around A is going to be 0. So I have to include point A in my diagram, but there's more going on than just what's happening at A. So really, I'm diagramming the whole ankle foot here in my picture. So I have a normal force acting on the foot, which I was told is 400 newtons. And that's acting 100 millimeters away from point A. And I have this Achilles tendon acting, so a force from that on the foot also. I'm being told that's 5 degrees from the vertical. And I don't know what its value is, that's what I'm trying to find. But I know how far away from A it is acting, or at least I can tell it's 200 millimeters above the ground. And to the left of point A, it's going to be 65 millimeters. Okay, so again, this is not acting through A, therefore it will create a moment about A. The normal force is not acting through A. Its line of action does not pass directly through A. Therefore, it will create a moment around A as well. All right, we're not necessarily in equilibrium. I'm not going to be summing forces, but I know that the net moment, there's no rotation around point A. The foot is not going to be rotating. It will not have angular acceleration. So for my equation step, I'm going to start with, I know that the net moment around A is 0. Now I have to find what are the things that cause a moment around A. In this case, again, we're looking at components of forces are going to be things that create a moment around point A. Right, so we want to look at all the forces that we have in our picture. We have, in this case, a reaction force, and we have this force from the Achilles tendon. I'll start with the easier one, which is going to be the reaction force. And I need a coordinate system here. I want to know what is the moment caused by the reaction force, or the normal force, around point A. So what I can do here, because this is already along the y-axis, our job is a little bit easier. I know that its value is going to be 400. And what I want to do is find its perpendicular distance to A. So what I do is I draw a line parallel to the force that goes through A. So that's just along the y-axis, or parallel to the y-axis. And what I do is I find this distance. That's what the perpendicular distance is going to be. So between this force, or this vector, and then the vector parallel that goes through A. That's the distance I use to multiply by the 400 newtons. So in this case, that's going to be 100 millimeters. This is in newtons Again, as long as everything is in the same units, we just want to be consistent. So I'll leave this all in millimeters, and that's okay. Now in 2 dimensions, what I want to do then is determine what's the sign. Does this create a clockwise or a counterclockwise moment around point A? So in 2D, what we can do, because we have to do it manually, is we want to put, say we're doing it on paper, if we put our pencil on the point where we're taking the moment about A, and then we just drag our finger in the direction of our force where it's located, what direction would the paper want to spin from the 400 Newton force? Right, if we actually physically did it, the paper will want to spin counterclockwise here. So this creates a counterclockwise moment around point A. Counterclockwise is positive. Right, so this will have a 400 times 100 Newton millimeter moment around A. Right, so that's just the moment caused by the reaction force. We will also have a moment caused by our other force, the force from the Achilles tendon. This one, though, is not only in the y direction or the x direction. So if I wanted to find the perpendicular distance, I would need to know what this distance was. Again, usually that's not easy to find. So alternatively, in 2 dimensions, usually the best thing to do is I break this up into its components. So I want to know how much of the Achilles tendon acts along its x direction and how much of it acts along the y direction. And we'll see why those distances are easier to find. So if I look along the y direction, that's going to be the y component of the force from the Achilles tendon. So that's going to be Ft, and the y component, based on this 5-degree measure, will be Ft cosine 5. This will be a force, so this will come out in newtons in the end. And then again, I need to multiply that force by its distance, or this component of force, by its distance from A. So I need to draw a line parallel to the force that travels through A, which is again this line, and then find that distance between them. In this case, that horizontal distance is the 65 millimeters. And again, I need to know, is it positive or negative? Is it clockwise or counterclockwise? If I hold down at A and I push along just the vertical component of the force, the paper is going to want to spin clockwise, which means that the vertical component of that force creates a negative moment around A. So that's the vertical component of the Achilles tendon force. I also then have the horizontal component. So what will the moment contribution be for the horizontal part of the Achilles tendon force? Right? It's going to be 0 because it acts along this line, and that line passes through point A. So its perpendicular distance to point A is going to be 0, in which case its moment contribution is also going to be 0. Right? So the vertical component of the tendon force and the ground reaction force both contributed to a moment around A. This horizontal component did not, and the reaction force did not have a horizontal component. So these are all the things that contribute to the moment around A, and I know for this problem that it's equal to 0. So the only thing I don't know then is the magnitude of the force in the Achilles tendon to maintain equilibrium. So I can solve this for that one unknown that's left. So the only thing I don't know is Ft. So if I go and solve for it, it is 618 newtons. Again, I want to reiterate, be careful. This is in millimeters and this is in millimeters, so it's okay. I wouldn't want to mix a meters and a millimeters. I won't get my force in the right units then.